Hey guys, so let's talk about section 5.4 today. We're going to look at right triangle trigonometry. I know last section was 5.1. We're not skipping 5.2 or 5.3. We're just doing 5.4 before that. So next week I will be doing videos over 5.2 and 5.3. So guys, let's get started. Today is the day we really start into the trig stuff. We are going to be using right triangles to help us define our trigonometric functions. So I'm going to start with a triangle. Of course, that is right. I'm going to label my A, B, and C. And I'm going to label this angle down here theta. And that's the angle that we're going to be finding trig functions for. So let's talk trig function. Sine, cosine, tangent, and we have three more that are the reciprocals, or those flipped over. We're going to learn all of them today. But what we know is that we're going to start with sine. We abbreviate this when we're working problems to just 3 letters. So the sine function is just going to be sin. And then when you're talking about a function, we know that it has an input and an output. The input of a sine function is an angle. You put in an angle and you get out a number. So this is where the input goes. I'm going to input our angle theta. So I'm looking for the sine of theta. Let's see what we get out. So if you're on a right triangle, if you're on a right triangle, the sine of theta is actually a ratio of 2 of the sides of the triangle. Sine theta is always opposite over hypotenuse. So we know what the hypotenuse is, we know how to find it, but let's talk about what it means to be opposite. So if this is your theta, the opposite side is the one that does not touch theta at all. So A and C are both touching theta, they're adjacent to theta. So the opposite side would be B. So if the sine of theta is opposite over hypotenuse, in this picture we have here, that would be B over C. Now, after we talk about sine, next, usually we talk about the cosine of an angle. You guys, so cosine, this is the whole word, but we abbreviate this COS. So let's talk about how to find the cosine of theta. So the ratio for cosine is adjacent over hypotenuse. So in our triangle here, adjacent, you guys, is the side that touches theta. Yes, the hypotenuse does touch theta, but remember that's called the hypotenuse. So when we're talking about the adjacent side, we're talking about A. So we're going to have cosine equals A over C. Then we have tangent. So tangent is abbreviated TAN, and the tangent of theta is opposite over adjacent. So notice tangent doesn't include the hypotenuse at all. Opposite over adjacent would be B over A. So you get really used to these ratios, but they are something you need to practice to get used to them. Which one goes on top, which one goes on bottom for which function, right? So you guys, we have the little saying, and if you've taken a trig class before, I'm sure you've heard it. We use the, I can't really call it a phrase, it's not even really a word, acronym, if you will. You guys, we have SOHCAHTOA. So SOHCAHTOA kind of rolls right off the tongue. It's easy to remember. And if you remember, the H. It's kind of silent here, so you have to remember. So this is so, but you know you can put an H on here, and this is also so. Same with the ka, and the toa doesn't have an H, it just says toa. So you remember so, ka, toa, and it helps you remember your trig ratios. So the S-O-H, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if you can remember SOHCAHTOA, you can even write it down as you're working these. You know the ratios are right here. So this is the sine ratio, the cosine, and the tangent, and that might help you. All right, so before we talk about the other three, I want to do an example with sine, cosine, and tangent on an actual triangle. Okay. So let's say I've got a right triangle. Let's say this bottom side is 6, the long side is 8, and the hypotenuse is 10. Let's say the angle theta that we're working with is down here. And I want to find the sine, cosine, and tangent of this angle theta. Notice I don't actually have to know the angle measure to find the sine, cosine, and tangent of that angle. As long as you have the sides, that's what gives you your answer, right? It's just the ratio of sides. So, the sine of theta, so sine is opposite over hypotenuse. So if this is our theta, opposite is 8, hypotenuse is 10, and I get 8 over 10. And then I can reduce this to 4 over 5. Cosine, adjacent over hypotenuse. So 6 is the adjacent side. So we get 6 over 10, or reduce it to 3 over 5. The tangent is opposite over adjacent. So that would be 8 over 6, or 4 over 3 when we reduce. So like I said, we didn't have to know what theta was. We just knew the sides of this triangle and how they work together. All right, so while I'm on this specific example, let me talk to you about the other 3 trig functions that we use. So the next on the list is cosecant. So it's one that you might not have heard of, you guys, but the cosecant, abbreviated CSC of theta, is the reciprocal of sine. So we consider these the most important to learn first because the other 3 are just these flipped over. You just have to know which one is which. So cosecant is the reciprocal of sine. Sine is opposite over hypotenuse, which means cosecant would be the hypotenuse over opposite. You take whatever sine is and you flip it over. In this triangle, hypotenuse over opposite would be 10 over 8. And reduce that to 5 over 4. And notice we could have just taken our sine that we already had and flipped it over and gotten the cosecant of 5/4. I'm going to have to erase a little bit. Okay, so that's cosecant. Let's talk about our next reciprocal function, secant. So kind of the same word, but without the co. Secant is the reciprocal of cosine. And I know it's a little bit confusing. We want to put cosecant with cosine and secant with sine. One way I like to remember it is when you're pairing up the reciprocals, you can only have one co per pair. So cosecant goes with sine because you can only have one with a co. Cosine has to go with secant because you can only have one co. All right, so secant is SEC of theta. Remember that cosine is adjacent over hypotenuse, so flip that over and you'll find that secant is the hypotenuse over adjacent. In this triangle, that would be 10 over 6 or 5 over 3. Again, we had the cosine. We found it to be 3/5. We flip this over, we get that 5 over 3. Our last one, guys, so we have 6 trig functions we work with in this class, and this is the last one. It's cotangent. So this one's easy to remember what it goes with. Cotangent is the reciprocal of tangent. One has a co, one doesn't, so that pair only has one co. Cotangent of theta. Well, if tangent is opposite over adjacent, then cotangent must be adjacent over opposite. So adjacent over opposite in this problem would be 6 over 8 or 3/4. And I know I erased it, but if you look back, we had a tangent of 4/3. That got flipped over, now it's cotangent. So really, if you know SOHCAHTOA, if you know how to find the sine and cosine and tangent, you can find these other 3 by flipping them. Like I said, all you gotta do is remember which one goes with which. Obviously, tangent and cotangent are an easy pair because they have the word tangent in them. But the others, remember, you can only have one co. All right, so you have some homework problems. They will start off with an example just like the one I did. It'll give you a triangle. It'll give you the numbers for all of the sides, and you find different versions of, or different combinations of these ratios. It's never going to ask for all 6. Sometimes it might say find sine, cosine, and tangent. Or it might say find secant and cotangent and cosine. You know, it can pick. I think it asks you to find 3 of them each time. But if you know how to find all 6, then you can definitely answer those questions. All right. So let's look at this example and talk about how to work through it using the ratios we know now. So it looks just like the example we did a second ago, except for we are missing a side. If you don't have, well, let's see what side this is. If this is our theta, this is the opposite side, right? If we don't have the opposite side, we can't find sine, we can't find tangent, and we can't find the reciprocals of those 2. So in this problem, it's going to be asking for a ratio that needs the use of this side. So we have to find the side first. This goes back to your geometry review. It's just kind of combining 2 things into one question. So let's say that this question says find the sine of theta. You say, okay, well, the sine of theta is opposite over hypotenuse, so that would be x over 5, but we have to find out what x is first. So on these problems, use the Pythagorean theorem to find your missing side. So x squared plus 4 squared equals 5 squared. So your a squared plus b squared equals c squared. And we solve from here. X squared plus 16 equals 25. Subtract the 16. And we get x squared equals 9. Square root both sides here. Remember, our square root is not going to be plus or minus when we're working with actual lengths because those are always going to be positive. So we get x equals 3. So I'm going to note that this side is 3. Before we find the sine of theta, this right triangle with sides 3, 4, 5 We see it a lot because it's what we call a Pythagorean triple. When you have side lengths that satisfy the Pythagorean theorem, but they're all whole numbers, those are special relationship triples. You don't have to know them. I'm not going to test you over them, but it would save you some time. If any time you were working with one of these triples, like let's say you were missing the 5, I could look at this without doing any work and say, oh, well, that's 5 because that's the 3, 4, 5. Or if we're missing the 4, oh, well, it's got to be 4 because this is the 3, 4, 5. As we come up to different Pythagorean triples, I will let you know that that's what they are, and so you can start remembering some of those relationships. So the 3, 4, 5, definitely going to see that a lot. It just saves you some time doing the Pythagorean theorem to find the missing side if you already know what it is. All right, so anyway, we're looking for the sine of theta, and theta is right here. I erased my SOHCAHTOA, but I remember it because it's an easy thing to remember, right? And I say so. Sine is opposite over hypotenuse. So opposite of theta is that 3 we just found, and the hypotenuse is 5. Do you remember we got this for the sine of theta on the last problem? But the sides weren't 3, 4, 5 then. They were different. I love doing these problems next to each other. All right, that's a horrible drawing. I'm going to have to fix that a little bit. These triangles are similar, so they should look exactly the same. That's a little better. This was our triangle last time, the 6, 8, 10. Another triple you can remember. This is the 3, 4, 5. I've got it a little out of order here. But anyway, you get the point. Guys, what is a relationship between 3, 4, 5 and 6, 8, 10? Well, isn't 6, 8, 10 just a multiple of 3, 4, 5? Well, yeah, so these side lengths have the same proportions as these do, right? These are bigger, but they're all twice as big. So it grew proportional to what it started with. So a little back to geometry review. These are similar triangles, which means this angle theta here, I'm going to have to fix my picture. This one's a little backwards. Well, dang it. Hold on. I drew this triangle a little upside down. This would be the theta we were looking at. Notice this theta and this theta are the same. My triangles are flipped because I don't know why, because that's how I decided to draw it. But the sine of this angle theta was 3/5. What's the sine of this angle theta? 6/10 or 3/5. You guys, when you have similar triangles, the angles present in those triangles are going to be exactly the same, which means their sines, cosines, tangents, all of them are going to end up being exactly the same. Sure, the side lengths are larger, but in the end, they will reduce to that same value. So think about that, this concept of similar triangles. All right, so we did get a sine of 3/5 there. I think it only asks for one value on these questions. We could find all 6 though, right? You have it in your power, in your abilities now to find any of the trig functions it asks for here. So that concept of similar triangles having the same angles, that's important to note. And it helps us realize that it's not the size of the triangle, it's the value of the angle. It's the relationship between the sides that's important. That's basically what these functions are, right? They're just relationships between the sides that this angle creates. So that's one thing I want you to be thinking about. It's not something I ever explicitly ask you a question on. It's just good to know to increase your understanding. And there's also something else that's really important I want you to get out of these right triangle ratios. So I'm going to draw a similar picture to the one I did at the beginning, where we have A and B and C. But instead of just labeling one angle, I'm going to label both of them. So let's call this angle down here, that should really be beta. I'm going to put alpha on top. You guys, let's call this one down here beta, and this one up here will be alpha. I want to talk about both angles because it matters. It matters which angle in the triangle you're talking about. Because, for example, we've used this one down here that we call theta. Now I'm calling it beta. Sine of beta, opposite over hypotenuse. That's B over C. But what if I had asked for the sine of alpha? Would it still be B over C? Well, no, because for this angle, A is the opposite side. B is adjacent to alpha. So you guys, it matters which angle we're talking about, and these angles actually have a really special relationship. The first thing I want you to think about, and I'll write it down and then I'll tell you why. I probably shouldn't use an and symbol in a math statement. So alpha and beta are what we call complementary angles. So guys, what does it mean to be a pair of complementary angles? Well, if you remember, complementary angles are two angles that add up to 90 degrees. How do I know that both alpha and beta add up to 90 degrees in this triangle? Well, you guys, I just need to know a little bit about triangles. You know that the sum of all three angles in a triangle equals 180. So that's something, again, pull that from geometry and remember that if you add up all three angles in any triangle, right, not right, obtuse, it doesn't matter. If it's a triangle, the sum of all three angles is 180 degrees. In a right triangle, 90 degrees of that is taken up right here. So how much is left over for alpha and beta? Well, 90 degrees, right? So alpha and beta in a right triangle always have to equal 90, which means they're complementary. I want you to keep this fact in mind as I introduce you to a few more facts. Let's find the sine of alpha. Sine is opposite over hypotenuse. So the sine for alpha, remember that's this one up here, is A over C. Let's find the cosine of alpha. For alpha, adjacent over hypotenuse is B over C. Let's find the sine of beta. The sine of beta, so now we're down here, opposite over hypotenuse is B over C. And the cosine of beta, adjacent over hypotenuse, is A over C. You guys, we have some repeating values here. Notice that the sine of alpha and the cosine of beta are the exact same value. Also notice that the sine of beta and the cosine of alpha are both B over C. They're both the same. This relationship is not a coincidence. It's because alpha and beta are complements of each other. So, let me give you a little summary of what I just said. It falls under the topic of what we call cofunctions. We can see it with sine and cosine, but there are other cofunction relationships out there with the other four trig functions. Cofunctions are pairings of trig functions. So here's what we just found. And I'm going to call it theta again. For any angle, not just the angle in that specific triangle we made. The sine of theta is always going to be equal to the cosine of what? Let's think about what we had here. Remember, alpha and beta are complements of each other. And I found that the sine of alpha was equal to the cosine of its complement. You guys, that Again, it's not a coincidence. That is always true. So the sine of any angle theta would be equal to the cosine of its complement. If you don't know an angle value, you can still find its complement. Remember, they both add up to 90. So saying 90 minus theta would be another way of saying the complement of theta. Basically, you take 90, take your theta away, and whatever's left over is its complement, right? So this is true. It means that sine and cosine are what we call cofunctions of each other. We have more, and I erased my triangle, so I can't express it with that triangle, but the other 4 trig functions pair up with each other also. All right, so if we were to find the secant of theta, it would be equal to the cosecant of its complement. So you guys, secant and cosecant are cofunctions, just like sine and cosine are cofunctions. We have one more to pair up the other two. The tangent of theta is equal to the cotangent of its complement. And you guys, the reason why these relationships exist are the same exact thing we saw here. It has to do with the angle down here and the angle up here being complements of each other. And when you go from one angle to another, the ratios flip, right? Opposite is now adjacent. Adjacent is now opposite. And that makes these change in the way that they do. So you guys, these are your cofunction pairs. And I know we just talked about the pairs of reciprocals, and these are different. But you guys, I like these because they make the names make sense. Why do both sine and cosine have the word sine in them? Because they're cofunctions. What's the cofunction of sine? Cosine. That's why they're named that way. What is the cofunction of secant? Cosecant. What is the cofunction of tangent? Cotangent. So if you ever wondered why they were named in pairs, this is why they're named in pairs. So we have the cofunctions. I don't want you to get that confused with the reciprocals. Those are a different pairing, but what I can tell you, and it might help a little bit, is that whether you are trying to pair these up with the cofunctions or the reciprocal pairs. So like when I say reciprocal, I mean the fact that sine and cosecant are reciprocals of each other, cosine and secant. No matter if you're looking at cofunction pairs or reciprocal pairs, there's always only one co. So you think about it and you say, okay, I can't pair cosine with cosecant. They never go together because there's always only one co. Another thing that's nice, look, tangent and cotangent, that's the same pairing as the reciprocals. This is the easy one. So whether you're doing cofunctions or the reciprocals, tangent and cotangent always go together. It's these other 4 that you have to be careful about. Just remember, there's only one co per pair. In cofunctions, the pairs have the same root word. Sine, cosine, secant, cosecant. And in the reciprocal functions, or the reciprocal pairs, they have different root words. So with the reciprocal, sine goes with cosecant, and cosine goes with secant. So cofunctions have the same root word. Reciprocal pairs have different root words, with the exception of tangent and cotangent, which are the same either way. So I know that was a lot, but you will get used to that. Cofunctions is probably something, even if you've had trig, you might not have talked about cofunctions before. Here's an example you're going to see in your homework that has to do with cofunctions. They're going to give you a triangle, and it's not going to have numbers. It's just going to be letters. So in this example that I pulled off of Alex, we've got a U, a T, and a V. They say this is angle T, angle V, and angle U. So we have all three angles and all three sides named. And here's what it asks for. It says, okay, what's the sine of T? Well, how do I find the sine of T, angle T? Opposite over hypotenuse, that would be T over V. And then it says, what is the cosine of T? Well, the cosine of T is adjacent over hypotenuse. It's U over V. I hate when they use U's and V's in the same problem because I have to be very careful about making sure they look different. Sometimes my U's and V's get very similar. So I'm trying to be careful about that. Then it asks for the sine of U. That is a big U. What is the sine of U? Opposite over hypotenuse is U over V. And then the cosine of U adjacent over hypotenuse is T over V. So you guys, basically they're wanting you to find that same relationship we found with alpha and beta in that example I just did. But this is all you do. So you actually put in the letters. You don't actually find numbers for these. You just put the letters in. A little practice on your trig ratios. And then it gives you a list. Let me give you a little example of what that list looks like. So what it says is it's like a little drop-down list and you have to pick which statement is true. So looking at what you just created and knowing what we know about cofunctions now, which one of these statements is true? Is cosine U the same as cosine T? Well, no, that's not what we said here, you guys. Is sine T the same as cosine T? Sine T, cosine T, definitely not. Sine and cosine are rarely the same value for the same angle. So you guys, these two, as you look at them, they're just not true. And you can verify that with this relationship you found. This is what's true. You know it's true because you can look here and verify it, but you also know because sine and cosine are cofunctions and T and U are complements of each other. So you pick the right expression, the one that is true, from that list. And then what you do is you use this information that you have, just information about cofunctions, what these relationships tell you, to answer a third part of this question. So yes, there's three parts to this question. We did this, we picked the right answer here, and then in part 3 of this question, it will actually give you a numbered example, so a specific example. And this one gave me this. It said the sine of 28 degrees equals the cosine of blank. How am I going to find that? You guys, you don't have to calculate the sine of 28 degrees on this problem. All we have to do is use the concept of cofunctions. Use what this whole thing is telling us. So the sine and the cosine here, those are cofunctions. What do I know about sine and cosine? I know that the sine of an angle equals the cosine of what? The cosine of its complement. So the sine of 28 will be the cosine of the complement of 28. So when you're doing these cofunction problems, if you're going from sine to cosine, you take whatever they give you here and do 90 minus 28. Find the complement of 28, and that's what goes here. So if we do 90 minus 28, what do we get? 62? So you guys, that's what goes here, is 62 degrees. And they actually already tell you that it's a cosine. You just have to put in the complement of the angle. So this is a lot about cofunctions. I've talked for quite a few minutes about cofunctions, so we are going to move on to something else. they're just so important. And if I have a personal bias about anything we teach in this class, it's this, you guys. This, I feel like it's so important. I love it so much. But yeah, so that's why I probably jabber on about it a little too long. Okay. So you guys, let's look at this problem. I have a triangle with a missing side length. I've got an S. So you guys, I don't know what this side is. It just told me it was side S. This long leg here is 16. And I actually know the angle here is 56 degrees. So that's interesting, right? In this problem, notice I don't know what the hypotenuse is, but it's not part of the question. You guys, all it wants me to do is find S. Now, knowing what I've known up to this point, I would say I can't find S, because to use the Pythagorean theorem, you have to know two sides to find the other side. I don't know two sides, I only know one side. So I can't use the theorem. This is not one of those special cases, right? It's not a 30, 60, 90 or a 45, 45, 90. How do I know that it's not one of those? Well, because I have one of the angles, it's 56. So, like I said, using the information I have up to this point, there's no way to find S. But now that I know some trig ratios, I think I have a fighting chance. So let's think about it. Think about the angle you have and the two sides that are labeled. Even though I don't know this one, what relationship could I use that I just learned that could help me here? You guys, this angle, this side is opposite of 56, right? And the S, what I'm looking for, is adjacent. Do I have a ratio that includes opposite and adjacent? I do. Now, I have tangent and cotangent. They both have opposite and adjacent in there. When in doubt, choose tangent over cotangent. So you guys, here's what I'm going to do. The tangent of any angle theta, I'm going to remember what that ratio is. It's opposite over adjacent, right? The TOA. Why don't we take this and fill in what we know about this triangle? So I know theta, which is weird because usually I don't know theta. But I do know theta, you guys, the tangent of 56. Well, what does it equal? It equals opposite over adjacent. So it equals 16 over this S. I'm looking for the S. Notice this S is the only unknown in the problem. While I don't just know the tangent of 56 off the top of my head, my calculator knows it. It is a known value. So you guys, this is known. 16 is 16. All I have to do is find S. How can I isolate this S? Well, I can use algebra, right? The first thing I would do is get it out of the denominator. So let's multiply both sides by S. Then I have S times the tangent of 56 equals 16. How do I isolate S from here? Let's divide both sides by the tangent of 56. So you guys, your trig functions, you can use algebra on them. Just treat it as one term. So I'm going to divide both sides by tangent 56. Notice, even though at any point I could have put tangent 56 into my calculator and gotten a rounded value, I am not going to do that until the very end. You guys, anytime you're rounding, do everything in your power to decrease rounding error. A lot of times that just means waiting to do any calculations until the very last step. And that's what I'm doing here. So notice, I've isolated my S and I found that S really just equals 16 over the tangent of 56. This is what I'm going to put in my calculator carefully. You guys, as you do something like this in your calculator and you have a trig function on the bottom, be extra cautious. I like to put this in parentheses, so I'm going to put in my calculator, wherever it is. So you guys, what I'm going to put in is 16 divided by, and then in parentheses, tangent 56. This one, I think it said round to the nearest 10th, so I will round to the nearest 10th, and what I get here is 10.8. So, side S is about 10.8, and that's what answer you're looking for. So, I used it in a kind of weird way, but I did use a trig ratio to find S. Now, you're not always going to use tangent on these questions. It depends on which side it gives you. What if it had given me, what if I didn't know the long side, but I knew the hypotenuse was, I'm just guessing here, don't take this to heart. Let's say the hypotenuse was 20. Which ratio would I use knowing what I know about this angle? Well, notice for this angle, then I would have adjacent and hypotenuse. So it looks like I would be using a cosine to find my answer on that one. So, like I said, you don't always use tangent. It depends on what sides you have. But when you set up the ratio and put in the sides and angles you know, you can solve for the one you don't know. So guys, I know I had mentioned at first we could have used cotangent on that one because cotangent is adjacent over opposite. I had both of those sides. So why did I choose tangent instead of cotangent? Well, mainly because I knew this was going to be calculator work, and finding the cotangent in your calculator is harder. There's a button for tangent. There's not a button for cotangent. So it's easier if you use sine, cosine, or tangent anytime possible. All right, guys, we've got one more example I want to do with you because you're going to see problems like this on your homework. And it's going to be a word problem. They're not all exactly the same backstory, if you want to call it. The one that pulled up for me was there's a house. I'm not an artist, so I'm sorry about this. So we got a house. It's a really good house there. And then it has this triangle off the side. And honestly, I can't remember exactly how the problem is worded. But no matter how your problem's worded, they all have a picture. So I think if you can just understand what the picture looks like, you can answer these problems. This one was something about a house and a ladder on it. There's some about an airplane, but they all have a picture. So you can understand what it's asking for. In this picture, I have this angle here that I don't know is X. I have this side, straight side here is 14, and the hypotenuse, or the ladder, or whatever it was, is 16. Okay, so my goal is to find X. Now, what would be something easy to find? Oh, I have 14, 16. I could easily find this side with the Pythagorean theorem. We don't care about this side. It's not important because it didn't ask for it, so I'm not even going to worry about that side. So I have to figure out a way to actually find the value of this angle. Like on the last problem, I'm going to look at the angle's location, look at the sides that I have, think about a ratio that fits that criteria. So according to this X, this is opposite and this is hypotenuse, right? So I'm thinking sine, opposite over hypotenuse. Let's write out the formula for sine. Sine for any angle theta is opposite over hypotenuse. Okay, let's put in what we know. Well, for one, I know that this angle is called X, so I'll call it X. I still don't know what it is, but I'm just labeling it with the X. I know the opposite is 14 and the hypotenuse is 16. So you guys, I know both of these values, but I don't know x. Okay, so the sine of some angle x equals this. How do I find the angle? So it just takes a little bit of thinking and a little bit of calculator work. Remember at the beginning, I said that all these trig functions, you input an angle and you output a number. So you input x and you get out 14/16. I could reduce that, but it's not really important right now. Okay, so I need to go backwards. I need to find some way to put in this number as an input and get out an angle. How do I take a function and switch inputs and outputs? You might not remember, but basically changing inputs into outputs and outputs into inputs, you take a function, you switch x and y around basically, is finding an inverse function. I need to find an inverse function for sine that will give me my answer of x. So inverse function of sine is actually called inverse sine. You guys, there's two ways you can see it written. You can see it like this, a sine with a little -1 at the top. So this isn't a power. It just means this is actually the inverse function of sine. Another way you can see it is arc sine. That also means inverse sine. So basically, what does the inverse do? Well, instead of you putting in an angle and getting out a number, you take the inverse sine of the number and you get out an angle. So if I was looking for this x, where the sine of that value is 14/16, I would actually find the inverse sine of 14/16, and what I would get out is x. So see how they're flipped around. Inputs and outputs are changed. You guys, the arc sine, it would be the same. These are actually the exact same function, just there's two ways to write them. So you guys, it looks like I need to find that button on my calculator. You guys, on your calculator, it'll look like this. It'll look like sine with a -1. It might not have its own designated button. It might be a second function on your sine button. That's what it is on my calculator. So when I do the inverse sine of 14/16, in my calculator, I do a second function, sine, and it gives me inverse sine. Then I put in 14/16. And I get my answer. So, like I said, your calculator is more than likely not going to say arc sine. It'll say this. But you find that button, you put in the value that you know, your answer is an angle. You guys, my answer is 61.04 degrees. Again, it'll tell you what to round to. But that's what I got. Make sure you can get that too. Since we are starting to use our calculator a little more, I want to make sure that your calculator is in degrees when it needs to be in degrees. Like today, everything we do in 5-4 is in degrees. But when it's in radians, or when we're doing problems in radians, you need to be able to switch your calculator to radians mode. My calculator is in degrees right now. But on my calculator, I push mode and I go down to that choice and I can click radians. Every calculator is different, so if you do have trouble switching from degrees to radians, because sometimes we will have to calculate things in radians, we can work through that together. Or you can Google it or something, I don't know. It's probably not that hard, but I just want to make sure we know that when we're using our calculator right now, we are in degrees. So I got 61.04 degrees as x. Now, this particular example was a sine problem. You might have one that you need to use inverse cosine or inverse tangent. Like say you didn't know that was 14. You knew this was 10. Well, you wouldn't use sine on this problem, right? You would use adjacent over hypotenuse. You'd be using cosine. Well, for cosine, you would use, it would say cosine to the little -1, inverse cosine, or arc cosine. And you guys, the same would work for tangent. Let's say that you just knew this information. Well, on this one, you would end up using an inverse tangent or an arc tangent. They all work the same way. Your calculator works the same way no matter what. So like inverse cosine is probably a second function of the cosine button. And this same for tangent. All right, guys, so I think this covers 5.4 though. This is my last video for this week. Next week, I'll be doing 5.2 and 3.